In this video, we'll continue our conversation about inner product spaces or vector spaces with an inner product by seeing that at least in the case when V is finite dimensional, there is a way that we can represent an inner product with a matrix. It's called a matrix representation of the inner product. Let's begin by looking at an example that we saw in the last video. That example was V, the vector space R2, and the inner product of two vectors U and V, given by this rather strange scalar expression. As an exercise to computing some of these inner products, and also to prove a much more important point, let's calculate the inner product of the standard basis vectors using this inner product. Remember that the standard basis of R2 is just a collection of these two vectors 1, 0, and 0, 1. So to begin, let's take the inner product of 1, 0 with itself. So when we do that, we get the following expression. So here U1 is 1, U2 is 0, V1 is 1, and V2 is 0. So using the formula above, we just get 1 times 1 minus 0 times 1 minus 1 times 0 plus 3 times 0 times 0, or just 1. Now let's try again with the second standard basis vector. For this one, we can see that with U1 is 0, U2 is 1, V1 is 0, and V2 is 1, we get the inner product of 0, 1 with itself to be equal to 3. Now there are two more I want to do. I'm going to take the inner product of 1, 0 with 0, 1. For 1, 0, 0, 1 inner product, I get negative 1. And then the last one is with the inner product of 0, 1 with 1, 0. So we could calculate that directly, or we can just recall that the inner product is commutative. That is, the inner product of these two is the same as the inner product of these two switched around. But we already calculated that directly above, so we can just write this equality, and this, of course, is equal to negative 1 from above. So we've calculated the inner product with all possible combinations of the standard basis vectors. Now I'm going to give these inner products names. I'm going to call them by lowercase c. I'll call the first one c sub 1, 1, because it's the inner product of the first basis vector with the first basis vector. Similarly, the second one I'll call c2, 2. It's the inner product of the second basis vector with the second basis vector. The third one, by this rationale, I should call c sub, can you guess it? 1, 2. And the third one I'll call c sub 2, 1. Just a naming convention, but I'm making it for a good reason, because now I'm going to take these elements, and they may look like it. I'm going to build a matrix out of it. Let big C be the matrix with Cij in its ijth position. Of course, we'll insert the numbers. This is just, in this particular example, this is in the matrix 1, negative 1, negative 1, 3. Now let U and V be two vectors. Staying with this example for a moment, let U and V be two vectors in V. Now let's remember that this vector space is just R2. For two vectors U and V in R2, let's take the following matrix product. I'm going to consider the matrix product U transpose times C times V. Now make sure this makes sense. This is going to be a 1 by 2 matrix. This is going to be a 2 by 2 matrix, and this is going to be a 2 by 1 matrix. So this matrix product is defined, and it'll should give us a 1 by 1 matrix, or just a number at the end. But we're going to rewrite this in several different ways. So now we'll write this in a more explicit fashion. U transpose will be the row vector U1, U2, and here V is the column vector V1 and V2. And here's our matrix C. But now we'll write out what C is explicitly. We calculated it up here. And now we'll take the matrix product of C and V1, V2. We'll take this matrix product right here. And that'll give us a 2 by 1 matrix, which is this thing right here. It looks like a square matrix, but this is just one entry here and one entry here. And so now when we take the product of the row matrix U1, U2 with this matrix, this is a 1 by 2 times a 2 by 1, we obtain the following. Matrix multiplication gives us this expression right here. Make sure you check it. Which, as you may have guessed, is just the inner product that we started with. So the moral of this story is this. There are evidently two different ways to calculate the inner product of U and V for this vector space and this inner product. We can either rely on the explicit definition of the inner product as given in the problem, or we can take U and V and insert between them a matrix C such that this matrix product gives us the inner product. But not any matrix C. This matrix C was carefully chosen and constructed to give us this result. Here's that moral. I'll write it down right here. V is a vector space with this inner product. Then we found that there does exist some matrix C such that the inner product of U with V is just given by U transpose CV. Since this is true, we sometimes say that C determines the inner product. Well, it may not be a great surprise that this method that we employed works in far greater generality. In fact, if V is any finite dimensional vector space with an inner product and an ordered basis, then we can always find a matrix which determines the inner product. We'll write the theorem down. So the setup for the theorem is this. Let V be a vector space with an inner product and some ordered basis. So we're fixing an ordered basis S with basis elements B1 through Bn. Note that clearly this set is finite, it has n elements, and so our theorem only addresses finite dimensional vector spaces. Then we will proceed as we did in the example. We'll take inner products of all pairs of basis vectors. We will denote by C sub ij the inner product of the ith basis vector with the jth basis vector. And of course, since we're taking all possible inner products, this will give us n times n, or n squared scalars C sub ij. And then we'll use these n squared scalars to build a matrix. Then two things are true. Oh, here's our matrix C, which we built. Then two things are true of C. First, you may have noticed in the example above that the off-diagonal entries of C were equal. That is, that the matrix C was symmetric. And this will be true in general. That's our first conclusion of the theorem. C is equal to C transpose, that is, C is symmetric. And the second property, that this matrix C represents the inner product, or determines the inner product in the sense we described above. C determines the inner product. What do we mean when we say that C determines the inner product? Well, what we meant above when V was R2 was we meant that the inner product of U and V was equal to U transpose C V. But this can't be what we mean in general now, because U and V aren't necessarily column vectors in Rn. Remember, we started with an arbitrary vector space. For example, V could be the vector space of polynomials. And if V is, for example, the vector space of polynomials, what do we mean by the transpose of U? So this can't be what we mean. We mean instead the following. We mean that the inner product of U with V can be realized by taking the coordinate vectors of U and V, taking the transpose of the coordinate vector of U, multiplying by the matrix C, then multiplying by the coordinate vector V. Of course, these coordinate vectors are with respect to the basis S, which we fixed way up here in the statement of the theorem. As we mentioned above, we say that C determines the inner product. We also use the following language. We say that C is the matrix of the inner product with respect to the basis S. Because, here's a brief remark, if you go back and look at the construction that we used in our previous example, it looks like the construction of C depends heavily upon the basis of S that we choose. So, if we fix an inner product and choose a different basis, then we may very well get a different determining matrix C.